So one topic we didn't get to last lecture was solenoids. So when you want to make a magnetic field for some application using a current, you typically don't use a long straight wire. Instead, what you do is you wrap up a wire around a tube, maybe around a cylinder of iron, which helps to enhance the magnetic field, and that's called a solenoid, just like you see in this picture. Alright, so for a solenoid, you've wrapped some number of turns of wire around a cylinder of some length. The magnitude of the field created by that solenoid, which is uniform inside the solenoid, is mu naught, the permeability of free space, times n, the number of turns of wire per meter. So if the solenoid is 1 meter long and there's 5 turns of wire, then that's 5 per meter times the current. To find the direction of that magnetic field, you use a right-hand rule, number 2. On the last slide, I'll show you an easier way to do this, so let's come back to that in a few minutes. Alright, now what the field looks like inside and around the solenoid actually is a field from a bar magnet. That was the answer to one of your checkpoints. And that bar magnet is oriented like so, and I'll show you how to find that using right-hand rule number 2 on the last slide. The reason a solenoid is so useful is because it's a magnet you can turn on and off. It can be a very powerful magnet, like an electromagnetic crane that you can use to pick up scrap metal. Again, turning it on and off is very useful because you can also use it to move things around. For example, in a solenoid valve, which is used in your car. So in a solenoid valve, there's a tube that you want liquid to move through, like this. And you can block that tube with a plug made out of iron or steel that's pushed down with a spring. And there's a solenoid wrapped around right here, so there's a solenoid turns coming into and out of the page. And when you run current through that solenoid, what it will do is it will draw that plug up against the spring, allowing water to flow through the tube. Very useful. Okay, so to go back to our chart to fill in a little bit more for electric fields versus magnetic fields, we know what the field lines look like around a positive charge. They point everywhere away from the charge. And that's the direction the force would be on a positive charge. For a current, the field lines make circles around them. So for a current pointing out of the page, you put your thumb along that current and your fingers curl around in the direction of the magnetic field. Here, going clockwise. Alright, there's one last thing we should fill into this chart. We know that opposite charges attract. What do opposite currents flowing? What do opposite currents do to each other? Currents flowing in opposite directions. So you have all the tools now. You have to use right-hand rule number 1 and right-hand rule number 2 to figure out how currents affect each other. What forces do they exert on each other? So let's look at this. On the left side of the slide, we have currents in the same direction. On the right hand of the side, we have currents in opposite direction. So you should imagine on the slide, there's 2 wires coming out of the page, and in this case, each wire is carrying current out of the page towards you. So let's think about that situation, the situation on the left here. So let's think about what is the magnetic field made by this wire on the left at the wire on the right. So to figure that out, and then once we know that, we can figure out the force on this wire on the right, we use right-hand rule number 2. So we take our thumb, we put it along this current pointing out of the screen, we extend our fingers over to this wire, and away from our palm, outward from our fingers, points the magnetic field, in this case up. So now we use right-hand rule number 2, because if there's a magnetic field here, there's a force on this wire. So what we do is we put our thumb along the outwards of the screen along the current, our fingers along the field, and outward from our palm points the force. And the wire on the right is attracted to the wire on the left. Of course, because of Newton's third law, they're attracted to each other. There's equal and opposite forces. And so wires carrying current in the same direction attract each other. Alright, so now look at the right side of the slide. Here we have currents in opposite directions. So again, imagine 2 wires coming out of the screen. The wire on the left carries current out of the screen. The wire on the right carries current into the screen. So again, we're going to use right-hand rule number 2 to figure out what is the magnetic field produced by the wire on the left at the wire on the right. So we put our thumb out of the screen along the wire on the left. We take our fingers and we put them right at the wire on the right, and again there's a magnetic field up. just like we figured out for the first situation. Now we want to figure out the force on the wire on the right from the magnetic field. It's carrying a current, there'll be a force. So in this case, we take our thumb, we put it along the wire into the page, our fingers along the magnetic field, and we find a force pointing to the right. Of course, again, because of Newton's third law, the wire on the left will feel force to the left, and this means that currents in opposite directions repel. So to fill in this chart then, what we have is that we have currents that are opposite in direction repel each other. Alright, so a summary of right-hand rules now that we've learned. The first right-hand rule we learned, right-hand rule number 1, was a right-hand rule that told you the force if there's a magnetic field present on a moving charge or a current. Alright, we learned you put your thumb along the velocity or the current, your fingers along the magnetic field, and outward from your palm points the force for a positive charge. Then we learned a right-hand rule number 2 for figuring out the field from a current-carrying wire, the magnetic field produced by a current-carrying wire. There's different versions of this, and I find it simpler to use different versions of this in different scenarios. So the one we had time to really cover in class well was the version of right-hand rule number 2 when you have a long straight wire and you want to find the field from that wire at some point in space. You put your thumb right along that wire in the direction of the current, and then you move the tip of your fingers to the point where you want to know the field, and straight away from your fingers, outward from your palm, points a magnetic field. And if you do this, and you do this at different points in space around the wire, you find that you get circular magnetic fields. In this case, it would be counterclockwise around the wire. I taught you a slightly different version of the right-hand rule number 2 for a current loop. And it's the same thing that works for a solenoid. So in this case, if you take your fingers and you wrap them around the wire in the direction that's carrying, in the direction of the current, then your thumb points in the direction of the magnetic field and basically the direction of the north magnetic pole associated with that loop of wire, that solenoid, because both a loop of wire and a solenoid make effectively a bar magnet, and that bar magnet has a north pole which points along your thumb. And then outside of that solenoid or that loop, you can just draw the field from a magnetic dipole from a bar magnet, and that's what the field will look like. Inside a solenoid, the field is very uniform and it points in the direction of your thumb. So everywhere inside the solenoid, the field points off to the left.